Dear student, welcome to the second video in the first module of college algebra class. In this video, we will get an introduction to the concept of relations and functions. Okay, so let me begin. In the previous video, we learned about the number systems. Of all the number systems, the one that we will use most often when it comes to the functions and the graphs of the functions that we will be dealing with will be the real numbers. Okay, and in the table that you see here contains what we call subsets of real numbers called intervals. Okay, remember real numbers. The reason we are using real numbers for functions is real numbers includes everything, right? Integers, rationals, irrationals, except imaginary, everything except imaginary, all real thing, real numbers. And so we can then use the values of the real numbers for all real world problems. Okay. And we sometimes need to deal with a part of the real numbers, not the whole thing. So those will be called, if the real numbers is the main set, these are the subsets. And what kind of subsets? Intervals. And the thing about intervals is you start at a point and you have an end point. You include everything in between. You don't miss anything in between. Then it is called an interval. Okay. Now the interval itself is of different types. How? The main question is it finite, first of all? Like, do you have a finite starting point and a finite ending point? Or you could be having a finite start point but going up to infinity, or you could be starting at negative infinity and ending at a finite point. When I say start and end, I mean from left to right. Okay. Or so that is one criterion. The other criterion is, what about the endpoints? See, when I say an interval, there is a start point and there is an end point. Sometimes you include the endpoints, sometimes you do not include the endpoints, or you might include one of the endpoints but not the other. All these things, right? Whether it is finite or infinite, and whether you are including the endpoints or not, and which endpoint creates these different types of intervals, which we are going to study here. Okay. And when we look at these intervals, we are going to look at set builder notation. Remember, we had an introduction about the set builder also in the previous video. The set builder way of writing, a set. And also we will look at their graphs, graphical view, those intervals. Okay. Let us start. This parenthesis here in the first interval that you see means that endpoint is not included. Okay, so I will write that here. Means endpoint, either way. Okay, whether it is opening one or closing one, that means endpoint not included. Okay, you might want to put that information in a box. So the first type of interval that you see here is called an open interval. If you do not include the endpoints, it's open, in that sense. Okay. So that means what? These are the numbers which are between -5 and 7, but not including -5 and 7. Therefore, in the set builder from now, using the set bracket, we write like this. X such that, what kind of X? minus 5 is less than x, right? It is between minus 5 and 7. And it is less than 7. Okay. Understand the meaning of the parenthesis, endpoint not included, and its implication when we write the set builder form. Now the same interval, if you want to represent on a number line. Okay. So the real number line always between starting at negative infinity, ending at infinity, arrows on two sides. Now you have this interval from minus 5 to 7. Say minus 5 is here and 7 is here. Use an open circle here, use an open circle there. The open circle means again those endpoints are not included and the interval between them from minus 5 to 7. Okay. In textbooks, you will find that segment that I drew with open circles and a line segment joining them, it is drawn on the number line itself with a different color, or it could be a little thicker, more bold. That is all right in textbooks because you can, do all the settings. What I recommend is when you write on paper, do it the way I'm doing it because for visual clarity, especially you are not going to use multiple colors, So show it separately from the number line for clarity. Okay. That was the open interval. Okay. What about the next one? On this side, on the left side, it is all the way from negative infinity and you are ending at negative 4. We still call it open interval. Okay. Although the thing with negative infinity you have to observe is you can never use a square bracket with negative infinity. Okay. Don't do that. Because that means you are saying that I'm including the negative infinity as a number, which is not the case. Okay. Negative infinity is an idea, right? It is a concept. It's a very, very, very large negative quantity. No finite number is going to be negative infinity. So you are never going to actually reach negative infinity or infinity. So those are not numbers and you cannot use a square bracket. So you will see that whenever you have infinity and an interval, it's always going to be with parentheses. The understanding is that, that doesn't affect the definition of open or closed. You look at the finite point to decide whether it is open or closed. And in this case, negative 4, the other endpoint is open. So the interval is open. Get the idea? Okay. And in the set builder form now, you can say this. X says that. Now you can write negative infinity is less than x is less than negative 4. Okay. No harm. And just the regular way how we wrote before. But then what I will do is I'll remove this. Okay. And understand that you don't have to say negative infinity is less than x, right? It is implied. Any negative infinity is less than any number. So you can just say x less than negative 4. Again, it's not incorrect if you write the full thing that I had written before. That's okay. This is, shorter and more precise. On the number line, now you are starting at negative 4, right? Open and to the left. Now what you do is you just show the arrow because it's all the way till negative infinity. Okay. Next, two square brackets, right? That is when the interval is closed. So you are including the 3 and 8 in that interval. And in your set builder form now, a small change will take place, right? Which is 3 is the left endpoint, but now you will say equal or less than x. Okay. So these are two different types of inequalities, The one that we used for the first two are called strict inequalities. So -5 is strictly less than x. Now, this is not strict. Okay. The another word for not strict is slack. If you want to just note down the jargon, no? It's called slack inequality. So 3 is equal or less than x now. In the same way, it is equal or less than 8 on the right side. And that's the closed interval. Okay. And you can guess now what happens on the number line. You can go ahead and draw. Think if the open interval was shown with open circles, what would you do for a closed interval? You will use solid circles or filled in circles. 3 to 8 like that. Okay. In the same way, the next interval now, you have parenthesis on the left, square on the right. So there are two ways. Okay, I think out in the textbook you might find in some textbook you will find it written as neither open nor closed because it's half open, half closed. I would prefer another terminology which I am writing here, or which is also more commonly used, and because it is more informative. Okay, we call this open closed. Okay, open on the left, closed on the right. Open closed interval. And go ahead and write the set builder notation and check with me. So it is strict on the left, slack on the right. And similarly, go ahead and draw the graph on the number line. Okay. Okay. There was one more concept of these intervals. Open and closed is one. The other one I was saying whether they're finite or infinite, right? I forgotten to mention about them. Let me write. So the first one here is finite. The second interval is infinite. I'm going to use F for finite and I for infinite, okay? But not making it very messy over here. That is finite. That is finite. So the finite here is not the amount, not the like number of elements in the set, okay? That is always going to be infinite. You have infinitely many numbers on any interval, right? How many numbers are there between 3 and 8? Infinitely many. The finiteness here is we're talking about not the finiteness of the set, finiteness of the length. Okay, so maybe I would do service. Give me a second. Sorry, I had to drink water. Okay, so I was saying we have to, so we're talking about the length of the interval. Okay, so I would do service. I think I was saying that by mentioning that here. It is the length of the interval that is finite or infinite. Okay, so with that idea, this next interval here is infinite. Okay, although it has a finite endpoint on one side, the length itself is infinite, right? It goes all the way till infinity. Okay, now this is closed on the finite side, and you would say it is open on the other side, right? So should I call it closed open? The answer is no. Okay, remember what I said earlier. When it comes to infinity, you cannot use square bracket anyways. But if I write, infinity on the right side here for this interval, what number is it on the right side that I am not including? Think of that. You can keep going any finite number all the way, right? There is no restriction on the upper side. So the definition of this interval would be still closed. Okay. Again, I'm saying depending on textbook, in some textbook you might find this mentioned neither open nor closed. In some textbooks or in some other literature, let me say, not just textbook, you might be reading a blog or watching a video, right? In some literature, you might find this mentioned as closed. I'm going with that because it makes more sense to me, okay, at least, right? Because you are including whatever the interval numbers are endpoints, 0 and infinity being an idea, you are including everything in between them, including the endpoints, right? Okay. So when I say including infinity, including everything large. So it is a closed interval. Okay. So the notation, we did one of this type earlier, so you can give it a try and check with me. X such that 0 is equal or less than x. Or you can say x is equal or greater than 0, doesn't matter. It's the same. And you don't have to mention the other side. Everything is less than infinity. Okay. On the number line again, same idea. You begin at 0 with solid dot and continue till infinity with an arrow. Okay. Now what about both sides? Infinite, that is basically the whole real numbers, right? Okay, negative infinity to infinity is all real numbers. Okay, so of course its length is infinite, and this one is both open and closed. Okay, now you might argue with me. According to what you were saying a second ago, this should be called closed, right? Because you are including everything. Yes, I agree with you. But there is also another way of looking at openness and closedness, which is a little advanced. I don't want to bother with you. Okay. Uh, Let me just put it this way. The second one in this list, we called it open because the finite side was open, right? The one that before this one, I don't know, 1, 2, 3, 4, the fifth interval in this list, we call it closed because the finite side was closed. Infinity had nothing to do with it, right? So with that idea, okay, infinity doesn't affect the closedness and openness, and both sides are infinity. Call it both open and closed. Okay. If you are interested in what I was saying about another concept of openness and closeness, a more advanced idea, meet me. Okay. And I will go over that with you happily. Okay, both open and closed. And what would the interval notation be? Just all real numbers. Okay, so what can I say? I'll simply say, you can say negative infinity less than x less than infinity. That's all right. I'll simply say x is real. Okay, that's all real numbers. So in set builder, you don't always have to do mathematical. Okay, you can sometimes just explain it briefly in one phrase. Okay, and what about the number line notation? It is all of them. So this time I'm just going to draw the number line. That's my interval. Okay, and finally you have an interval. You have a subset. I won't say interval. You have a subset which contains two intervals, right? And the symbol that you see in between here looks like U. Okay, it's called the union. That's the union symbol. Okay, in set, in the set theory, that's the union symbol. It means union, combining. Okay, so you are including all the numbers up to 2, and then after 6 you are missing the things in between. Okay, so you want all the numbers up to here and after that. So what do we do? You combine them, and now this is not one interval. Okay, this is a subset of real numbers, which is a union of two intervals. If you look at both intervals, each of them is open on the left, and on like the left side interval and the right side interval, both are open intervals. So as a set, not as an interval now, okay, the length is infinite, and as a set, it is an open set. So let me write that clearly. It's an open set, okay. And how would you write the notation? Set builder. This is important now, okay. You have to mention both the things, right? X says that x is less than 2. Then you also want to include the numbers more than 6, right? You say or x is greater than 6. That word is very important, okay? So I'm going to highlight here so you won't forget. X is less than 2 or x is less than 6. X is greater than 6. Don't use the word and, okay? Because it would be then a contradiction, a false statement. How can x be less than 2 and greater than 6? So it's either x less than 2 or x greater than 6. The word choice of word is very important there. And on the number line now, you have two things, right? You have negative, no, at 2 and towards left here, at 6 and towards right there, both open. Okay, all right, that's a very good discussion on intervals we did there. Let us do some problems. The three sets are given to you in set builder form. You have to rewrite them in interval notation. Okay, if you have been following, it should be not that difficult. 5 is not included, 9 is included, open, closed. 5 to 9, parenthesis when it is strict inequality, not included, square bracket when it is included. X says that x is greater than 0. Okay, remember greater than 0. So on the right side, so 0 is the left endpoint now. And nothing on the other side, so up to infinity. And the last one here, I created that example just to emphasize the fact that sometimes you can be given an inequality in a different order, right? Now, instead of saying x is greater than 7, here it says 7 is equal or less than x. So if you can directly process it in your mind and write the answer, that's fine. But if it helps you to understand when x is written on the left side, do that. Okay, rewrite it. So you can say x is equal or greater than 7 here. See, 7 is equal or less than x means x is equal or greater than 7, right? Then you understand that we are starting at 7, including 7 equal or greater than, and all the way till infinity. Okay. Now, just because you see equal or less than symbol there, don't write negative infinity to 7. That is a common mistake. Okay. You have to understand, what values of x are we including here? Equal to 7 or more than 7, right? So 7 and right of 7 on the number line. Okay. So we discussed, the subsets of real numbers which we will need to deal with, with when we deal with most of the functions. Now we are ready to talk about functions. We start with the idea of what a relation is first. Okay, a function has to be first a relation. We'll talk about that soon. And then what are the two components of it? The inputs and outputs, right? We call them domain and range. So what you are seeing here, this set, again, note that, okay, it's a set. What you are seeing here is a relation. So a relation is a set. Okay, a relation is a set of what? Ordered pairs. Okay, so there are pairs here, 1, 2, 3, and 4. 4 pairs, and they're ordered. Ordered means it matters which is first and which is second. Okay, and all the first elements are called domain elements. DOM for shortcut. The domain of the relation R. So when I write this symbol here, you have to, it is read as domain of R. Okay, the domain of R here contains the, see, the domain itself is a set again. Okay, A, B, C, and D. Domain is a set, the range is a set, the relation is a set. Domain is a set of elements, range is a set of elements. The relation is a mapping, right? From here to there, here to there. It shows that matching. So it's going to be the relation is a set of ordered pairs in which the first element is the domain element, second element is the range element. So the range of R here is the second elements, 1, 3. There is again 1, which I'm going to skip. Okay, that is an important thing there. If you never had an introduction to sets before, then I have to mention that here. Do not repeat elements when writing sets. Okay, so I wrote it as a instruction here. Do not repeat elements when you're writing sets. It is more like a what you call convention, or not a. It is implied. Okay? Even if you repeat, even if I were to write 1, 3, 1, 2, you will automatically understand that to be 1, 3, and 2. Okay, even if you write with repetition, it really doesn't count. Okay, so it won't be incorrect, just redundant. We don't do it because the concept of set is not about how many times. It is just a question of whether it is in or not. Okay, so very interesting thing. You have domain with 4 elements and range with 3 elements. right? And there is this relation. Okay. Now, a typical ordered pair denoted by x comma y, the domain consists of these x values, all the first elements. Similarly, the range consists of the y values. Okay. So that is relation and domain and range. So let me again summarize that and in this way. So how is a relation formed? Let me put it that way. You have a set of elements which will be the input or the domain elements. You have another set of elements which are the output or the range elements. And you create this mapping, what we call, okay, the word I've been using is mapping, okay, which we are going to say soon more. Mapping. What is that mapping? Every input element is mapped to something, right? In the output. Possibly every. Okay, we don't know. In a general relation, everything may not be mapped either on this side or that side or both sides. So let's say some elements in the domain are mapped to some elements in the range. That is that whole mapping, that structure would be called a relation. Now, the one that you saw here, the first example that we saw about a relation, that is one way of writing it, right? As ordered pair in the listing notation, we say we list all of them. There are other ways to represent. You could represent it graphically. Okay, on the left side, you see here, it's a relation in a graph, right? How it is a relation? There are x values and y values. If you follow that graph at any point, let's say I choose this point, it has an x value and y value 1 2 3 1 2. So this is 3 comma 2. Okay, so the input is 3, x value is 3, y value is 2. So like that, every point on that gives you one input and output. So it is a relation. Okay, infinite number of ordered pairs. Okay, so it won't be possible to list them. There are infinitely many points there. So we will represent that with the equation and all that. We'll come to that later. Okay. Right now, we want to write the domain and range. Now, what is the idea of domain? The x values, right? We said here, the domain consists of x values. So look at this. What are the x values? On this side, -4, I'm just not saying open, okay, I'm circling that. -4 here and 4 here, including, right? It's touching that line point. So including -4 and 4. So the domain we write here would be the closed interval, -4, 4. Interval, right? Now we need the intervals to represent the domain of this graph. And similarly, you can see the range are the y values from -3 to 3. Okay, so domain and range from the graph. Another way to represent relations is mapping diagrams. Okay, and again, especially it is possible either if the set is finite or even if it is an infinite set, it is countable, what we call, okay, like natural numbers, distinct numbers. And there is a clear rule, right? How a number is mapped to the other side. Then you can use this mapping diagram. For the relation on the left side, there are infinitely many points. A mapping diagram would not be a nice way to represent it. It will be confusing. Okay, there are infinitely many points, and how many you are going to write and how you are going to show a pattern. So for the function, or sorry, for the relation on the left, graph is the best way to represent it. For the relation on the right, you can still represent graphs. It will only be few points on the graph. A mapping diagram is more visually intuitive and clearer here. Okay. And what does it say? The domain now is a finite set. So we don't use interval. It's not everything from 2 to 17. 2 is the smallest number here, 17 is the largest. So you are not going to say that the domain is from 2 to 17. That would be incorrect. Why? Because we are not including numbers in between, right? So it's only few numbers, 2, 3, 5, 11, and 17. You don't have to write in the order, doesn't like you could just list them. Similarly, the range will be 7, 1, and 20. I'm emphasizing the fact that you don't have to order them. Okay. You can just list them. All right. What you will notice is just writing the domain and range doesn't tell you much about the relation. Okay. Understand that. If I were to tell you, I have a relation in which these are the domain and range, it won't be enough information, right? Okay. Some information, it's not completely blank. There is some information, but it doesn't tell me how they are mapped. For example, 2 is also mapped to 1 and 5 is also mapped to 1, right? So that is not coming out by mentioning domain and range. So you need to mention the ordered pairs, or you need to mention a formula, or you need to give a mapping diagram. You have to do some way to represent the relation. Okay. The question then is, we have been using the word relation here, but we will be studying functions mostly, right? So the question is, when does a relation become a function? A function is a special case of relation in which every, okay, that word is important, every domain element has a unique image. Okay, so the question we asked was, when is a relation a function? If you satisfy this condition, it's everything about domain, okay, focus. Both the words that I wrote there are about domain. So every element in the domain, that is the left side on the mapping diagram or the X values in a graph, for every element in the domain, there should be one unique output. Okay. If that condition is satisfied, it's a function. So to clarify, emphasize, I'm breaking this down into two parts. That means two things. Every domain element is mapped. No domain element has two distinct images. Okay, so with the word meaning of the word unique, you have to understand. It means the same element in the domain cannot have two different images. Okay, then it becomes a function. So of course, every function is a relation, right? Function is a special kind of relation, but not every relation is a function. So the definition that we used here, every element should have a unique image, that can be applied or visually seen when you look at a mapping diagram, or analytically if you look at ordered pairs. You can try to figure out if every element is mapped, and if there is no repetition in the of the domain element. How do you see it graphically? Graphically, this concept of, every element has a unique image, converts into a test called the vertical line test. Okay. What is a vertical line test? I will illustrate that over here. Look at the graph on the left side. If I were to draw a vertical line here, it intersects at one point up there and one point down here. It intersects at two different points. So that means it is not a function. Okay, it fails the vertical line test, we say. I'm going to write that here. Fails the vertical line test. And what is the vertical line test? That means if a vertical line, any vertical line intersects at only one point in the graph, then it is a function. Okay. And on the right side, so you can use the vertical line test when you have the graph of the function. Otherwise, you can go with the previous, the other, analytic definition. Let us discuss, the mapping diagram here, whether it is a function or not. Every domain element must have a unique image, right? So let's see. First of all, every element here is mapped. So the first condition is taken care. The second condition, are their images unique? And I'm discussing that here because there is some clarity needed. Okay. If you see, 2 is mapped to 1, 5 is mapped to 1, 11 is mapped to 7, 17 is mapped to 20, 3 is mapped to 20, right? So you might wonder, you might think it's not unique because I see more than 2 elements going to the same output. Again, that's not the way to look at it. Okay, the way to look at it is, the concept of that uniqueness is there one element which has 2 different images? Like, is like 2 going to 1 and also 2 going to 7, then it violates that uniqueness. The image of that 2 is not unique. In this case, the image of 2 is unique in the graph that we are given here, in the function relation that we are given here. Image of 2 is unique and image of 5 is also unique. The image turn happens to be the same. 2 is also mapped to 1, 5 is also mapped to 1, but for each of them individually, for 2 it is unique, for 5 it is unique. There is only one output, right? So all domain elements here have unique outputs. Okay, it is a function. Okay, so keep that clarity in mind, what uniqueness means. Okay, uniqueness does not mean you cannot have the same image for 2 different elements. Uniqueness means the same domain element should not have 2 different images. Okay. All right. We'll do some practice problems where you will see whether things are unique or not, whether the uniqueness is satisfied or not. Determine the domain and range of each relation and tell whether the relation is a function. Assume that a calculator graph extends to infinity. Okay, so like, when there is a graph given, you have to assume that it continues to infinity forever. Okay, that is the assumption. Okay, let's do it. For each of them, I'm going to write on the right side here, domain and range. Domain is the set of all first elements. Range is the set of all second elements. Okay. And the question, is this a function or not? You have to check. 8, 5, 9, 3. No domain element is repeated, right? So every domain element has a unique image. hence it is a function. I'll put a tick mark when it is a function. Check mark. Okay. Next, the domain. You can go ahead and do it on your own now. Right? Don't have to repeat that 0. And the range is 5, 3, -4. And when ordered pairs are given, this is a telltale sign. Okay, if your range is larger than domain, it's not a function because something must have repeated, right? And you notice that 0 is mapped to 5 and 0 is also mapped to -4. It's not a function. Okay, going back to what I was showing you, talking to you about the mapping diagram earlier, let me illustrate that now. You have 0 and 1 in the domain, 5, 3 and -4 in the range. And what is our function doing? It's mapping 0 to 5, 1 to 3, again 0 to -4. When that happens, okay, that same domain element is mapped to two different outputs. It's not a function. Okay. Moving on. What do we have here? When it is given like this in the tabular form, you have to understand the x values are the domain elements and the y values are the range elements. And domain is only one. Okay. Just the single element 1. But you don't write just the number 1. You have to use a set because domain and ranges are sets. Okay. Write them as sets. Even if it is only one element. Obviously not a function. Okay. And why? Because the same element 1 has all those images, not unique. And the next function, you have to write in small fonts now. Domain is 11, 12, 13, 14. Range is -6, -7. See, other values are repeated. Okay. Is it a function or not? Yes, it is a function. Why? Because the range elements are repeated and that's okay. Domain elements do not repeat. Okay. Given the graph of the relation on the right side, is that a function? And when graph is given, we use the vertical line test. You already have one vertical line here, the axis that itself shows you. If you want, you can draw one more. You don't need many lines. Okay, one line is enough. If there is one point for one line, if it fails, it's not a relation. Okay, so clearly it's not a function. So the graph is not a function because it fails the vertical line test. But what are the domain and ranges? Let's write that. And if you see here, the point that is marked here, x is -9. In the calculator, you have to see that, okay? X value is -9 for that, right? So the x values are the domain values. And because it's a parabola, what we call, okay, like that, it passes through that point, so the domain D touches -9, so including -9, but on the right side, so from -9 to infinity. And what about the range? And if you look at the range, those are the y values, and the idea is the graph continues forever in the same pattern, right? So it's going to expand. That means it's going to take negative y values and positive y values, all of them. So the range in this case is just all real numbers. If you want to write in interval notation, you can say negative infinity to infinity. Okay. All right. In the first problem here, find f of 5, it says. Find f5 in problem 1a. Now this is understanding the meaning of functions. Okay. Let me zoom out. So you can see it. In this function, what is f5? And I will highlight. When I write f of 5, this is the meaning of this notation. Okay, when I write f of 5 here, the function value at input 5. Okay, we write like that. The input is 5. What is the output? And output is the y value. Okay, do the same thing. But next, g of 0 in b. And then we observe that 0 is mapped to 5 and 0 is also mapped to negative 4. So our answer is going to be a set now. So in this case, we make a distinction. Okay, for problem 2 here, f of 5, we just said it's 4, it's one value. But g of 0 is not just one value. There are two different values. So you have to put them in a set. Okay, 5 and negative 4. And find fa and fb plus 1 and 3x given fx equals 2x minus 3. Okay. This problem here is crucial in understanding how functions are applied analytically. Okay. So the equation is f of x equals 2x minus 3, right? So the way you understand that is whatever input you give to it, x is the input. That input will be multiplied by 2 and then 3 will be subtracted from that result. Okay. You have to understand a function as a machine, That is one of the best ways to understand the concept of function. X is like your input. The function does some processing and it produces the output. So this machine here, what does it do to the input? That is the definition of the function. Okay. So in this case, what does it do? It takes that x and multiplies by 2, right? And then 3 is subtracted from whatever you get. That idea is used now here to write the answers. F of a, if your input is some particular number a, you would multiply that a by 2 and you would subtract 3, right? If your input is b plus 1, understand here, the b plus 1 itself is your input. So you multiply that b plus 1 by 2 times b plus 1. Now use parentheses, right? The b plus 1 itself has to be multiplied by 2 and then subtract 3. And after that, you can simplify. That will be 2b plus 2 minus 3. So 2b minus 1. Okay. And let me erase the machine representation of a function. Finally, f of 3x. Right? The input is now 3x. Okay. So that 3x will be multiplied by 2 and 3 will be subtracted. 6x minus 3. Okay, the input is multiplied by 2 and 3 is subtracted. Okay. Next question. If f of 2 is 9, identify a point on the graph of f. Suppose, now we don't know anything else about the function. Okay, only thing we know is when the input is 2, the output is 9. From that, can we get at least 1 point on the graph? Answer is yes. And that 1 point is when the input is 2, the output is 9. Input is the x value, output is the y value. So the 0.29 will be on the graph. Okay. This is for your practice. The next one, please write your answer and check with me. Okay. When the input is -1, the output is 2/3. Okay. Here is a word problem. The function f gives the number y in thousands of radio stations on air during year x. So here's the function. The x values are the years: 1975, 1990, 2000, 2005, 2012. And the y values are the number of radio stations in thousands. Okay, so 7.7 here means 7.7 thousand radio stations. Okay, use it's in a country in the US. Use the mapping diagram to represent f. First, mapping diagram is this, the two circles. Okay, I'm going to have a tough time writing here. I'm going to maybe go to the right side here. Or let me first write the years and we'll see what size of the oval I need. Okay. I need 1975, 1990, 2000. Give me 2012. So that is on my left side. And I have 7.7, 10.8, 12.8, 13.5, 15.1. Okay, and then I realized I missed out on one of them. That is 2000. There's 2005. And there's 2012. Okay. Here. Here. And we also sometimes represent the function itself by a separate arrow like that, just joining the two ovals, and then you map the individual elements, 1975 to 7.7, like that. That's the function we have. So that will be a mapping diagram. You can use an arrow. The arrow direction of the arrow indicates, what is input and what is output. You can put that at the tip of the line segment or in the middle, it doesn't matter. Okay, as long as you point from input to output. So that would be part A, mapping diagram. Evaluate F2000. And you can look at the function itself or look at the mapping diagram. Is 12.8. That's how we write. And what it means, I'm just going to say it in words, okay? You understand? It means in the year 2000, there were 12.8 thousands of radio stations in that country. Okay. Identify the domain and range. And domain, range. I'm going to just skip that part here. Okay. You know what to write. All these numbers. Okay. These numbers will go in the domain here. And those numbers will go in the range there. You'll separate them by comma. Okay. All right. We are done with that. In the next lesson, we will talk about linear functions. See you then.